Hi, John McElroy here, talking all things automotive as always. Today we're going to be talking with Scott Bailey and John Fuerst from a company called Tula, T-U-L-A, because they've come up with, I think, a pretty interesting innovation here, wherein instead of just continuously feeding electricity into an electric motor, say like in an electric car, if you send it in pulses, not continuously, the motor actually doesn't use as much electricity. Scott, John, I don't know if I described it right, but does that sort of capture what you've done here?
Yeah, go ahead, John.
I would say yes, absolutely so. And the next insight would be just to say that our technology works at low loads, and it recognizes the fact that at, let's say, medium loads, as you increase the load on an e-machine, the efficiency goes up. And therefore, delivering low torques with more efficient, higher torque pulses, which average out to the lower torque, nets you electricity savings.
Well, what is it about sending this in pulses and controlling the torque that makes it more efficient?
What makes it more efficient is that the loss curve of the e-drive goes up fairly steeply at very low torques. So the losses are going up fast, but as you go a little bit further, they go up more slowly. And therefore, you can pulse at these higher torques at lower relative losses instead of running steady state at a lower torque with higher relative losses. And on the average then, those pulses, because in between those pulses, there's zero losses because we shut off the drive. On the average, you use less energy to deliver the same result.
And how are you sending these electric pulses? I mean, what's controlling it?
Well, we have an algorithm that we overlay on the basic e-drive of the vehicle, and the basic e-drive is already running a PWM system of 5K or 10K, or 10K being 10,000 hertz frequency, and we overlay on that a lower frequency pulsing strategy. And so the underlying control of the vehicle's drive system is already positioned to execute our relatively slower strategy in, let's say, normal course of business, and we just overlay our strategy on top of the control system, and you get this efficiency benefit.
And I want to get into that more too, but Scott, let's talk a little bit about Tula. I mean, the reason I'm even talking to you guys is you've got a track record. I mean, you got product out there. You're not just somebody who's come up with some fancy idea and is trying to sell it. You guys, Tula, are the ones who invented dynamic skip fire, which GM uses in its V8 engines and I guess most of its trucks and SUVs. That it calls dynamic fuel management or something like that, right?
Yeah, in the GM application, yes. Yeah, Tula calls it, John, we call it dynamic skip fire. And I'm actually going to link this into a couple of the comments John Fuerst made just a moment ago. Tula as a company has really from our founding been based and focused on efficiency, improving efficiency of machines. I'll use that very general description. Our initial work was on internal combustion engines, and by improving efficiency, you also got an extremely important side benefit of improving emissions. So there's an environmental aspect to this too. Nevertheless, we did start with dynamic skip fire. The idea was to find a way to operate the internal combustion engine more often near its optimal efficiency. So there, it wasn't a pulsing strategy, it was a strategy of firing a cylinder when you needed to and skipping perhaps the next 2, 3, 4, 8, whatever it was needed, firing events, and then firing again. So from a control standpoint, the philosophy is fairly similar to what John described for dynamic motor drive. But in the case of the internal combustion engine, of course, you have these discrete cylinder firing events. So that's why we call it dynamic skip fire, because we'd make a decision every time a cylinder was coming up ready to be fired, to fire or skip. ultimately you have to deliver the torque that the vehicle or the driver is demanding. And you also have to do it in a way that the driver and the vehicle have no idea that anything different is happening. And that's a big part of our intellectual property, frankly, is getting the NVH characteristics of that control scheme to a point where the operator and passengers in the vehicle really have no idea that anything's happening. Now, in the case of our major application of dynamic skip fire, you're right, it was with General Motors. Nearly all of their full-size trucks and SUVs with V8 engines run Tula's dynamic skip fire. And we're very proud to have that kind of a track record. There's more than 3 million of those vehicles on the road right now. But even more significantly, from an environmental standpoint, each of those vehicles is saving on average 1 ton of CO2 emissions each year. So that from that beginning, we did get this control philosophy, I'll call it that, of saying, well, electric motor propulsion system also has a motor map. It looks different than its IC engine counterpart, but there is a region that is optimal efficiency. How can we take advantage and run that motor more regularly, more fully in optimal efficiency versus just accepting that at lower loads, as John described, you have to take low efficiency with that. So the link went from a control philosophy from internal control engines down to electric propulsion.
Mm-hmm. Got it. So John, what kind of efficiency improvements are you talking about?
Well, first of all, we always look at the full cycle test. I mean, if you look at a particular point, this point or that point, you can come up with double-digit figures that we try to make a point of not talking about. We talk about cycle benefits. So WLTP, for example, we're looking at a range of fractional percent, as low as about 1/3%, up to about 2%, given the right application of a wound rotor machine, IGBT power electronics, and we can get up close to 2%. On other cycles, and by the way, the other cycles generally are better for DMD than the WLTP. So the China light duty cycle, we get more benefit, maybe up to 50% more. So the 2 becomes kind of a 3, and the 3rd becomes kind of a 1/2 or a 0.6. But even some of the steady state cycles as well, we can deliver more benefit. But bottom line, what we're saying is on WLTP, between 1/3 and up to 2%, depending on application and drive topology.
Okay, that's the world light test procedure, light vehicle test procedure?
Light duty test procedure, light duty test procedure. So world harmonized, some people say, right? WLTP or WLTC for cycle.
Yeah, and the C being the China one, right?
Well, CLTC is China. Sometimes we say WLTC as in cycle instead of China. And sorry for that confusion.
Yeah. And then, you know, the EPA one is what? FTP 75 or something like that?
FTP 75, right. And that one also is more forgiving than the WLTP. So again, we'll have more benefit there than we would on the WLTP. But we're using that one because we feel it's kind of a global benchmark and a common point of reference. But essentially on all the other cycles, we deliver a bit more.
Okay, so I'll throw this to both of you. Why should the auto industry get excited about a 2 or 3% improvement in electric motors?
Well, I would say mainly it's good value. And in terms of the size, and I'm jumping right away to DMD. Why should they be excited about DMD? Of course, everybody likes efficiency, but it's not free. The thing about Tula's DMD is that in terms of price, cost per percent improvement, it's very competitive. It's about 1/3 of what the industry is paying for SiC efficiency, for example. And there's a lot of details to work through, but bottom line, what we've said is we want to license our technology and we want to license it competitively so that people get interested. And our pricing model says we want to charge about 1/3 of what SiC costs to get the same efficiency benefit. Scott, please.
Yeah, let me just interject, but Scott, I want to get your input too. SiC
Yeah.
being, of course, silicon carbide, and that's
Thank
one way
you.
to get more, efficiency. But yeah, Scott, what did you want to add there?
Well, two things. First, the other thing in terms of our pricing strategy, because this is a software solution, we have the opportunity, I'll say it that way, to price consistent with the value we deliver. So we don't have I'll say it, a fixed price because we have X amount of material costs and X amount of overhead. We have the flexibility to make sure that what we're asking the customer to pay is consistent with the value that they're receiving. And in a hardware-based solution, frankly, that's not always so easy to do because you end up with so much more of your cost structure that's somewhat fixed, if you will. So that was one point. The other point is 2 and 3% for maybe some members of your audience, John, that doesn't sound like much. But if you start with the basis of an average vehicle today has a electric vehicle, let me be clear, has a battery that is probably at least $8,000 in price. So if you think about a 2 or 3% savings on an $8,000 battery, and you want to keep the range the same, you're going to save anywhere from say $160 to $240 a vehicle.
What you're saying is you can actually make the battery a little bit smaller and keep the same range.
You can. Now, you maybe don't do that on day one or every vehicle, but that ability is there. You either get the range that you would like to have, or you can take cost out of your system, or both, depending on, you have more design choices. Let's put it that way.
Yeah. And John, you were mentioning before too, when you were citing these efficiencies of wound motors, i.e. motors that do not use permanent magnets, i.e. motors that do not use permanent magnets with rare earth minerals in them, which is something that so many automakers are looking for these days.
Exactly. I would say it's a worldwide concern regarding cost, regarding environmental concerns, as well as socio-political concerns. The magnets are problematic and they're costly. And of course, their performance is great. So that's why they're everywhere right now. But what we're seeing is the global auto industry, everybody's looking at a wound rotor alternative, which means copper windings on the rotor poles instead of having magnets there permanently. And the wound rotor technology offers some cost improvement. It offers elimination of these problematic rare earth metals. It offers very close to, let's say, similar, getting close to the same efficiency. And we at Tula are raising our hands saying, hey, add DMD to that wound rotor solution, and you're going to be equal or better than the permanent magnet design. And those of you who are spending money on SiC, we know it brings efficiency. It also maybe is an enabler for 800 volt systems. But in the IGBT space, where you're going to save all of that cost of SiC, DMD is there to provide most of the benefit, most of the efficiency benefit of SiC. So we think that as electrification is going to reach everybody, high volume, lower cost, lower price, competitive, let's say mass market vehicles are going to think about going away from permanent magnet, going to wound rotor, save some money, maybe not going to silicon carbide, keeping IGBTs. And right there, double ESM and IGBT, that is the sweet spot application case for Tula's dynamic motor drive. So that's what we think is going to happen out in the marketplace, and we're here to help make it happen faster.
Yeah, and that dynamic motor drive, DMD, as you keep talking about, is just a little piece of software code, right? I mean,
very small.
Nobody needs to
piece.
retool anything. You don't have to
Right.
validate all these other suppliers or anything like it. It sounds to me like it would be relatively easy for an automaker to incorporate this into their EVs.
I would say yes, but for sure there's going to be plenty of man years of effort. Not 100. Probably closer to like 10 sort of thing. But of course, you have to calibrate the vehicle, and you have to address noise and vibration concerns that can occur when you're pulsing something. You got to do it in a way that the vehicle tolerates it and make sure that the driver and the passengers never notice it's going on. And we've got a couple demo vehicles that we think prove that that's totally doable.
Well, just so the audience knows, I drove your demo vehicles, and if DMD is truly on board, I could not notice the difference whatsoever. There was some graphs on the center screen demonstrating that was what was going on, but seat of the pants, I couldn't tell anything that was going on. It was invisible to me.
Well, then we did our job adequately, I guess, John. I would like to build a little bit on the point John made. There is an investment of time and effort, certainly, particularly for the first application for an automaker or large tier one supplier for their first application of DMD. But from there, the other advantage we see is it's highly scalable. Once you've adapted your systems and incorporated DMD code into your larger, more comprehensive control scheme, it's fairly easy to apply to other applications across your portfolio. Yes, there will be some amount of calibration work, but in terms of proving the technology, getting the coding right, all of that work, you really only need to do that one time, which we think is also another advantage.
Scott, can you do this with existing computing power, or do you need to add more to a car for it?
The computing requirements are small, and there's so much compute power in the car right now. It's not that there's zero, but the load on the overall compute capacity of what's in today's car is very, very, very small. John, what are we talking? 100K of memory or less?
Less than 100K of memory and maybe about 2% of the compute or less. So it's not a big load.
Yeah,
sorry, go ahead, Scott.
No, I was going to say, so in total, whether you're thinking about the impact on it from a memory or, compute cycles, relatively minor impact.
So you've been showing this to automakers, right? What's been the reaction, and when do you think we could see something like this in production?
Well, we have shown DMD to a number of the automakers around the globe, frankly. We anticipate first production later this year.
No kidding. Wow.
Now I got to be clear, that's in China for a Chinese application of the technology. And frankly, I think the world understands fully at this point, the Chinese have been very committed, very aggressive, and committed to all forms of increased efficiency and improvement of their EVs. So for us, it was a nice fit because adopting a new technology is very, very open. And frankly, the Chinese are pretty fast. But we're also engaged pretty comprehensively with suppliers and automakers in Europe and also in the U.S. But it's a mix. Each market has a little bit different challenges, a little bit more certainty or less certainty about where the technologies go and where the automakers are. So we're obviously adjusting, and I'm not going to name names necessarily, but adjusting our strategies appropriately in line with what our customers are committed to do and willing and able and open-minded to.
Yeah. There may be one other advantage to your system that you're not even aware of. John, you had mentioned how automakers are looking to go to SiC, silicon carbide, to make their electric motors more efficient. Well, as you both know, electric motors can throw off a lot of electromagnetic interference. And there's been a lot of controversy over them wiping out AM radio, or automakers not wanting to go to the effort of protecting AM signals from electric motors. I'm told silicon carbide will interfere with police, fire, and emergency radios too. So if you can give automakers a solution that obviates the need for silicon carbide, I think you got another argument in favor of DMD.
Yeah.
Noted.
Yeah.
Noted. Not fully validating that, but noted. Thanks, John.
That's great. Anything else I'm missing here? Anything else you want to add?
From my side, nothing else but appreciation that you kind of put your nose into Tula and had a look around and took the time with us. And appreciate the chance to talk to you about DMD, John. Thank you.
John, the only comment from my side is we're obviously committed to efficiency. There's a number of questions throughout the industry of, well, are we just at a speed bump on the progress to all EVs, or what's the right interim strategy, and are hybrids a better solution, et cetera, et cetera. With DMD, we think we do have a interesting and flexible solution, whether you're looking at a pure battery electric vehicle or a plug-in hybrid. The impact of DMD in terms of helping that propulsion system become more efficient, it's agnostic to whether it's a pure BEV or a plug-in hybrid. And we're also a little bit agnostic to the timetable. We know certain regions are going to go faster and more aggressively than others, and we're in the enviable position in one sense of being able to adjust our efforts and targets accordingly, because we haven't had to build a $3 billion battery plant or something that you need to get into production and start earning a return on your capital real quickly. So we're excited about the role we can play throughout the industry, and really appreciate the opportunity to tell your audience a bit more about it.
Real good. Yeah. No, I think it's real exciting. I love the fact that you've come up with a little bit of software code that can make an electric car more efficient. I mean, that in and of itself is a great story.
Yeah. Thank you very much.
Yeah. Thanks,
Thanks
guys.
a lot, John.